If you plot this velocity autocorrelation function versus time, on the y-axis we have the velocity autocorrelation function, and the x-axis we have time. Then for a dense gas, this typically looks something like this. The time and this of course starts at 1 because the initial velocity is v0 here. So the value starts at 1 and then eventually decays to something around 0. So the time taken to reach for the velocity autocorrelation function value to become 0 is called the correlation, or more commonly the relaxation time. This is the time taken for the system to lose the memory of its initial velocity. This is how it looks like for a dense gas. For a liquid, it looks a bit different. It goes like this. The reason for this dip where the velocity autocorrelation becomes negative is the so-called cage effect. In a dense system such as a liquid, the particles are very close to each other. So if my particle of interest is moving in a particular direction, it hits the cage formed by its neighbors, and then the direction of its velocity is opposite to the initial direction. So because the direction of the velocity becomes opposite, so this value becomes negative, and therefore the correlation coefficient becomes negative for a dense liquid. Also, the kinetic theory of gases predicts that for a dense gas, this decay here should be exponential, but in fact it is found that for dense gases and liquids, this decay is not exponential but decays a bit slowly. The reason for this slow decay of the velocity autocorrelation function is the so-called vortex effect. So liquids have the so-called vortex effect. So if this particle hits this particle will have a velocity like this, or at least a component of its velocity like this, and eventually because of this vortex, this particle here will hit this particle in this direction, which means that it gets a push in the direction of its original velocity, which means that the velocity autocorrelation function will decay a bit more slowly than expected. This was one of the main results from early simulations of these spheres. Just like the velocity autocorrelation function, we also have the rotational velocity autocorrelation function, which is defined as c omega omega as a function of time. The definition is very similar to the velocity autocorrelation function, except now we have rotational velocities instead of normal linear velocities. Now the Fourier transform of this rotational autocorrelation function can be directly compared to experimental spectra such as IR, Raman and NMR. And this comparison is quantitative, at least for simple systems. So to summarize, what do we learn from velocity autocorrelation functions? One, we learn about system dynamics. Now, if I want to mention that the integral of this curve, the area of this curve, is also related to the diffusion constant by the so-called Green-Kubo relationships. You can check this out in any textbook. Velocity autocorrelation functions, the integral under the curve is directly related to the diffusion coefficient. And that's how you learn about transport coefficients. From the Green-Kubo relationship. And finally, the Fourier transforms are directly related to experimental spectra. So this was